Right. So today we're very happy to have Yifan Wang from NYU, and he will tell us about topological interfaces and generalized gauging.
Thanks for the invitation and thanks for the introduction. It's a great pleasure to be back to UCLA to tell you about our recent work. It's based on this paper that we put out with students such as Wang and Quentin at NYU, and also encouraged to look at this very nice paper from Jendi and friends that appeared shortly before. There was some overlap between our work and this work, but in this talk, I'll focus on the part that's not in overlap. And you're of course welcome to ask Jendi about the further details in this paper. And I should also point out there's the paper that appeared on the same day that studied a similar subject. I could also say that one of the students from Wang is on drama this year and is excellent. All right, so let me start with some brief motivations. So the goal of this talk is to kind of explain these two notions in a very concrete context of two-dimensional CFTs. The first notion is about topological interfaces. That's interfaces, a special kind of interface between different two-dimensional quantum field theories. And another notion is the notion of generalized gauging that, in a sense, generalize the usual discrete orbifold that you're familiar with in the 2D, in particular 2D CFT. And in this talk, we'll see these two notions go hand in hand. And in particular, the first perspective give you a very nice physical picture to think about gauging generalized symmetries, in particular symmetries that are realized not by invertible objects like groups, but rather by non-invertible generalizations known as topological defects. Let me first start with some broad motivations. I should say that this is a Blackboard talk, and I hope if you have any questions, you can speak up, and also happy to take further questions after the talk. Okay? So don't be afraid to interrupt me. So the first kind of broad point I want to make is that symmetry is very powerful, especially in the context of quantum field theory. This is something that you have encountered in many particular contexts, particular problems in quantum field theory. For example, symmetries leads to selection rules, observables that you study in quantum field theory in the form of award analyses, and also a particular fine feature of symmetries known as anomalies, total anomalies, can give rise to stronger constraints on the dynamics of quantum field theory coming from those symmetries. And the way to detect those anomalies, the efficient way to detect those anomalies is to couple your symmetry to background gauge field and consider the procedure known as gauging, okay? And consistency conditions involved for this process will give you a way to detect those anomalies. Okay? But also, this gauging procedure on its own is a useful tool that can use to generate new quantum field theories from the existing quantum field theories. In particular, most of the quantum field theory I know, interesting quantum field theory I know, are constructed from gauging, starting from very simple theories like free theories. Of course, in those contexts, typically we want to do gauging, want to implement gauging for continuous symmetries. But in this talk, we'll be focused on a case which is under better analytic control that involves discrete symmetries. Now, having made the point that symmetry is extremely powerful, of course, we want to look for the most generalized notion of symmetry. And this, here we come to this point that in recent years, there's a major paradigm shift in thinking about symmetries. And this is the point already alluded to in the beginning, where the most general notion of symmetries are given by objects known as topological defects. We will shortly review this notion in the concept of two dimensions, but broadly speaking, the usual properties that you like about symmetries, like conservation laws and so on, they are captured by this topological property of the corresponding defects. And in the conventional setup, you can think about the topological defects as defining the charge operators for the corresponding symmetries, the unitary charge operators. And these symmetries, as we learn from studying various examples, that in general they obey fusion rules. as topological defect, there are diffusion rules that are not invertible. Okay? And this leads to the notion of non-invertible symmetries. Okay? In the sense that they're no longer represented by unitary operators acting on your Hilbert space, but rather by operators that are not necessarily invertible. And then very nice property, practically speaking, a very nice property of symmetries is that symmetries are rather algebraic. And this is a notion to be contrasted with the vast richness of quantum field theory that's coming from analytic properties of observables. Okay, depending on locations, depending on continuous modulus. In contrast to that, the properties of symmetries are rather rigid. And this rigidity is what led to the enhancement of power of symmetries, in the sense that you can often deduce constraints from symmetries without knowing the full details of quantum field theory. And by that, you will still be able to make very non-trivial statements that tells you what kind of dynamics the QFT can support, knowing those algebraic symmetry properties. And again, going back to this point of gauging, is that as a procedure, you can implement any symmetries. It also has this algebraic feature. And as we'll see later on, this will be tied to rigidity property associated with the topological interfaces. Okay. The key takeaway message from the last point is that the rigidity of symmetry is what made it possible of this kind of deriving these constraints in a practical manner. So let's now be, just now we're being kind of broad. Let's now be more concrete and focus on a particular context where we study symmetries and this procedure of gauging. That is in two-dimensional QFT that I denote as T. This is a two-dimensional TQFT, two-dimensional QFT. And with symmetry, I'll characterize as CT, okay, which you can think about as the set of topological defects in a given quantum field theory T. Okay, and to be even more concrete, let's focus on the case is a two-dimensional CFT. Okay, in particular, I'll consider the special case, which is the case for usual interesting QFTs that are unitary and compact, meaning there's a discrete spectrum. So, for example, the Luvial will not be an example. And also, I'll focus on the case of a CFT, unitary compact CFT with unique ground state. Question? Yes.
So, how much of what you are going to say can generalize to non-unitary CFT? QFT, for instance.
So many of that would have a direct generalization to a special kind of non-unitary CFTs. So this is a funny thing. So when we speak of a non-unitary CFT, we have in mind some very special example like Liang, but those are really lamppost models. We don't really have a good control over the vast class of how non-unitary QFT can be.
Okay. Let me mention one problem.
So for a special class of non-unitary CFTs, what I'm going to say have a direct generalization, but for the most general non-unitary CFT, I don't have.
Okay, let me mention one something. So
yes.
Even if you want to gauge invertible symmetry,
yes,
or non-invertible symmetry,
yeah,
whether the system is unitary or not will affect that. But like how many possible ways to gauge it?
It will affect. Yeah, that's right.
But you are focused on like unitary.
I'm not saying what I'm going to say. A modification of what I'm going to say can apply to a special class of non-unitary CFTs, but I'm not saying the answers I will present directly tell you the answer for those cases. Okay. All right. Because many of the conditions I'm going to write down are motivated within this class of CFTs and preserving these properties. Okay. In particular, preserving the fact that you have a unique vacuum. All right. So let me emphasize about this notion of CT that you may also worry about. So I said, like intuitively speaking, this should be thought of as the set of all topological defects in the theory. Okay. But mathematically speaking, we don't really have a good way of thinking about this object. And the most practical approach is to take a subset of this topological defects within this full set of topological defects. And that, if it's finite, is often described by a fusion category. Okay. And the basic objects in this fusion category are topological defects. And we're in 2 dimensions, so these topological defects are lines. So I'll call them topological defect lines, or TDLs for short. And the fact they're being topological is the following. So I can represent, because we're in 2-dimensional, we can represent these topological defects as curves on the blackboard and with orientation, and label such a topological defect at L. And the fact it's being topological just means that in the presence of some other insertion that you might want to insert in your observable, the correlation function will not change as you deform the shape of this topological defect, as long as it does not cross any insertion. And more generally, if you have other topological defects around, this is operator identity. As long as the deformation you do to your topological defects does not cross any other insertions given by local operators or junctions between the topological defects. Okay, it's known as isotopic invariance. And this topological property is what replaces the usual conservation property of symmetries in this more general context. Now, where this notion of fusion comes in, it comes in that when you have multiple topological defects, let's label them as Li and Lj, okay? And they're transferred to one another. And you can imagine, because they're topological, you can imagine that they are pushed together arbitrarily close. And looking at it, this configuration from far away, it's given by a single topological defects. And if you have a basis of topological defects within this set, the subset subspace, then this can be expanded into the basic ingredients known as simple topological defects. So let me denote this set as generated by simple topological defects, meaning those ones that can no longer split further. Then this fusion product can be represented as a direct sum with some coefficient that keep track of genesis of the simple topological defects. And emphasize that these numbers are required to be positive integers for a reason that will become clear shortly. That's coming from the fact that we're not just caring about arbitrary topological defects, but those that satisfy a locality property. Okay. We'll come to that shortly. But this is what's capturing the fusion structure associated with the topological defects. Now, so far, it's rather abstract. Okay, we haven't really used any property of the CFT that I put down for you. Okay, let's now come to the physical features of symmetries realized in the concrete CFT. The first of all, interesting symmetry should act non-trivially on the objects in your CFT. In this context, local operators. So in particular, TDLs. They would act on local operators just like charge operators would do. And the way acting on local operators, you can imagine that you have a local operator over here at some position x, and you can encircle it by a topological defect line as follows. Okay. Because this defect is topological, you can shrink it down to the point where this operator is inserted. And this will lead to another operator at the same space-time location. Okay, it's going to be a point-like operator because I can shrink it all the way down to this point. Okay, and knowing the fact that this L is topological, means in particular is transparent to the stress tensor, it will tell you that this operator and this operator, a priori they're different, they must have the same space-time representations. So in the context of two-dimensional CFT, these two operators needs to represent the same Virasoro representations. So in particular, if this operator is Virasoro primary of dimension h, comma h bar, okay, this better be operator with the same left and right scaling dimensions. And by the radial, by the conformal mapping and the radial quantization, you can translate this picture to the more conventional picture you think about symmetries as unitary operators acting in the Hilbert space. By going to the cylinder, where this local operator is not represented as a state on the cylinder. Okay, we quantize from the circle. And then this topological defect line just hugs the cylinder. Okay. And this naturally leads to this linear action of this topological defect represented by L hat as a linear map. Acting, this is a linear map. Acting on the Hilbert space S1. Okay, this is a particular state in the Hilbert space S1. Okay, and mapping this particular state to the state corresponding to the transform operator. Okay, and the key difference between a generalized symmetry represented by a topological defect that's not necessarily invertible is that this operator in general is not going to be unitary. Okay, for the invertible case, this operator as a linear operator on the Hilbert space is unitary, but in general it will not be. In particular, you can detect the fact that it's non-invertible by focusing on how this operator acting on the vacuum. So acting on the vacuum, which corresponds to identity operator, okay, by the radial quantization, and by the fact that we have a unique vacuum, okay, and this property, we preserve the space-time representation, it has to be proportional to the vacuum, up to a number. And that number, you can easily convince yourself, is nothing but just the expectation value of the corresponding topological defect. Okay? Because in that case, you have nothing inserted in here, and you can shrink down the topological defect all the way to the origin, and what that computes is nothing but the expectation value of the corresponding topological defect. And this number has the following property. It has to be bounded from a below by 1. That's a consequence of unitarity. So this is already a property that doesn't hold in the non-unitary context, even in the vanilla non-unitary CFTs like the Yang models. Furthermore, the non-invertibility is equivalent to the fact that this L can in general be not equal to 1. So in other words, it's invertible if and only if the expectation value of the topological defect is 1.
Okay.
If it's bigger than 1, it's necessarily non-invertible.
So can it be a complex number?
Sorry?
Can the expectation
Cannot.
be a complex
Yes,
story?
cannot. It cannot.
It cannot.
Yeah, for unitary context, it cannot. So this is the condition coming from unitarity. Okay. This you can derive from what I'm going to say next, from the locality together with the existence of Hilbert space, which you don't have in the non-unitary context in general. For especially non-unitary CFTs, you may still have a notion of Hilbert space that is kind of slightly funny in the sense that the inner product may still not be positive definite, but in most general cases, you don't even have a Hilbert space.
What keeps you from just rescaling?
Sorry?
What prevents you from just rescaling?
Yes, very good question. We'll get to that. That's coming from locality. Okay. Very good questions. Of course, what I discussed over here, this picture of looking at the topological defect is nothing. There's no really difference between looking at some operators acting on some space given by some quantum mechanics. Okay, the special property of the topological defect coming from locality comes about by looking at the following operation you can do with topological defect. That leads to this notion of topological. That leads to this notion of a defect Hilbert space. So the idea is the following. If you have a local quantum field theory, okay, it means that you feel free to, if you have local quantum field theory, have the most general observable of the local quantum field theory on the general manifold. Let's work in the Euclidean signature. You can feel free to cut the open manifold in codimension one by codimension one spatial slices and quantize the theory on the codimension one slice, and then glue them back together. Okay. Of course, when you cut in different spatial slices, you will find different Hilbert space interpretations. But because it's the same observable and by locality, you're guaranteed to get the same Euclidean observable. There's a generalization of that locality property in the case with a topological defect, and that's what we mean by a local topological defect. It means the requirement for observable decorated by topological defect, you are free to cut either across the topological defect or parallel to topological defect. And there should be a natural Hilbert space interpretation either way that produce the same observable. And that when you cut your underlying space and manifold parallel to topological defect, you get to this kind of picture. But instead, you can imagine that you cut in a way that's transverse, that crosses the topological defect, that leads to this picture. And the demanding this has a natural Hilbert space interpretation that leads to a generalization of the usual twisted sector for this general topological defect. There's no notion of the defect Hilbert space. Okay? So over here, this represents the general state. This represents the quantization on the spatial slice that's punctured through by the topological defect. And the state over here is a state in this defect twisted Hilbert space, which I emphasize as a superscript M. Okay. And again, by the same conformal mapping that leads to a relation between the local operator and the states on the cylinder, you can relate this to an operator that lives at the end of the topological defect L. And they are in one-to-one correspondence. And the condition of the symmetry being faithful here represented by the topological defect L requires the corresponding operator to have a strictly positive total scaling dimension. Okay. Of course, by unitarity, you already know that H bar are individually bounded from below by 0. Okay. The requirement of the operator, the requirement of topological defect being faithful requires the topological defect to not be able to end topologically. That means the endpoint operator has to have a non-trivial scaling dimension, and that implies it has to have strictly positive total scaling dimension. Okay. If it were to end topologically, it means that you can break a topological defect line into two freely, okay, and then contract it from the other way. And this way, any operator will have to be uncharged under the corresponding topological defect. That's why faithfulness implies that. Okay. All right. But so even though a single topological defect cannot end topologically, okay, which is another way to say that is that there's no, so you can also think about this picture as this operator as a junction between a topological defect line and the trivial line. So I write as identity. Okay, you always have a trivial topological defect that corresponds to inserting nothing. Or you can think about it as identity. You can think about this operator as a defect changing operator from this non-trivial topological defect to identity. Okay. So the same statement here is telling you there's no topological defect changing operators from just non-trivial topological defect to identity. Okay. But there are topological defect changing operators for more general configurations of topological defects. The natural generalization of the picture on the left is to consider, instead of a single simple non-trivial topological defect in a temporal direction, you consider multiple of them.
Sorry, I have a question.
Yeah. Go ahead.
The faithful symmetry condition follow from the unique market condition?
Sorry?
Separate. Does the spatial symmetry condition follow from the unique vacuum?
No, it does not follow from the unique vacuum condition. It follows from together with unitary.
The fact that the endpoint exists, does that rely on the unique vacuum?
So if you do not have a unique vacuum, then definitely the endpoint. So if you do not have a unique vacuum, it says that if you have an endpoint, if one endpoint exists and you have a family coming from the all this vacuum operate, this dimension 0, 0 operator in the series, but not the other way around. Okay.
If you have like a one-form symmetry, so like a local operator,
Yes.
this would be like an operator with a.
So if you already have an endpoint, you can just put any topological operator in the bulk, and they give you another endpoint. But you need to have the starting point. Okay.
Well, I guess the question is more about a converse. So I think the questions are sort of in the spirit of asking whether the only way that,
Yes.
that a line can break open is if it's the condensate of some topological point on.
That I'm not totally sure, but that sounds reasonable. Because if you were to derive the converse statement the way that immediately does assume, let's use the fact that there's a unique vacuum. Yes. Okay. All right. So the more general picture of the left-hand side is that you have multiple topological defects on your cylinder running in the temporal direction. Okay, so here I draw you an example where you have 3 of them. And there's really no difference from this picture in the sense that here you're just dealing with the Hilbert space. Okay. You're dealing with a state in the Hilbert space that's twisted by the corresponding topological defects. Okay, and again, you can run this game of doing the cohomol mapping, and this leads to corresponds to some operator that leaves you at the end of this topological defect configuration that join at this point. And in this context, okay, we have multiple topological defects in the temporal direction. We can focus on the subspace, and we can do the same restriction over there, but the answer to be non-trivial. You can focus on the subspace where H and H bar are of the corresponding states or of the corresponding operators are strictly 0. Okay, and this subspace is known as the topological junction space. And this space captures the kind of topological operator that they can use to glue different topological defects together. And a particular case is when, so I define given a topological defect, okay, I define its orientation reversal as equivalent to the topological defect with opposite orientation, okay, as operator equation. Then just by starting from a topological defect and bend it back, okay, you see there's a topological junction between the topological defect and its orientation reversal, and correspondingly, this junction vector space is always non-trivial. Okay. What this junction vector space is telling you about topological defect operator that live on a given topological defect L, and that always includes the identity operator that you inherit from the bulk. Okay. And this in particular is isomorphic to C, just one-dimensional, if the topological defect line is simple. It's indecomposable. Okay. This is something that may also fail in a non-unitary context. All right. So this space is going to be very important, as I mentioned, just in a similar way that you can construct a gauge theory, a gauge field background gauge field for discrete group-like symmetries by transition functions, which you can think about as topological defects for Euro symmetries joined in a way that's consistent. That's coming from compatibility conditions on the transition functions. These topological junctions are what replaces this compatibility conditions between transition functions in the generalized case to allow you to build a general background for a non-invertible symmetry. So these are building blocks or building a background for generalized symmetries, which is the starting point to think about gauging this corresponding symmetry. And I should say, I will not have time to explain it in detail, but I should say in passing that if you look at topological junctions involving more topological defects, for example, a topological junction involving 4 topological defects, okay? So this is a similar picture over here. There are preferred bases for this topological junction vector space. And the change of basis between this preferred basis, so for example, there are 2 different, so this is represented in general by a cross. Okay? I'm just being kind of cavalier about the orientation. So let's, for example, assume there are to be all self-do in the sense that you don't need to carry the orientation around. So a general vector in this junction vector space labels a vector, a junction vector over here. Okay, that's one topological junction. And because it's a vector, feel free to scale by a number. So representing the corresponding vector by V. Now there are different ways to think about this topological junction. You can think about a topological junction as resolving this fourfold junction into 2 threefold junctions as follows. I label them in the same way. Okay, because they're topological, each of them is topological, feel free to collect them, and that leads to this factorization give you a basis for the topological junction over here. Using the basis of the topological junction here, tensor product with the topological junction over here. And there's another preferred basis that's given by factorizing this fourfold junction in the other way. Okay, and these 2 different bases of thinking about this topological junction vector space, of course, have to be related. Okay, and in a unitary quantum field theory context, this change of basis is represented by a unitary matrix that's known as F symbol. Okay, and this F symbol further obey consistent conditions where you consider consecutive change of basis operations in the higher in the topological junction involving higher number of external points. And that's known as the Pentagon equation. And it's known that the Pentagon equation completely solves all the consistent conditions in this change of basis for higher point topological junctions. Okay, but this is a side remark for the experts. All right. But the fusion category that I mentioned in the beginning is nothing more than just the topological defects together with these topological junctions that whose change of basis are the F symbols that solve the Pentagon equations. That's what the fusion category is. All right, so having kind of reviewed the notion of topological defects that describe generalized symmetry in 2 dimensions, let's now talk about gauging and how to think about generalized gauging for this non-invertible guys. So we will start relatively slow by first reviewing what gauging means for the traditional, for the conventional invertible symmetries. But in this new language. Okay, so in general, what do we mean by gauging is that we want to look for a subset of the TDLs, the defect lines, supported in a given quantum field theory T. Okay, and we want to say we want to ask if there's a consistent process to proliferate these topological defects that give rise to some background. Okay, and sum over these backgrounds. And whether that leads to a consistent QFT T-prime, which we usually refer to as gauge theory. And this arrow you can heuristically think about as projecting 2 sectors which are invariant under this subset of TDLs. Okay, this is the most intuitive in the case when you have discrete group-like symmetries. So just to put our feet on the ground, let's consider a special case when the symmetry is a Z2 group-like symmetry. I think everyone knows what that is. And in the category language, the corresponding fusion category is usually denoted as follows, but don't be afraid about the notation. It just means a Z2 symmetry, okay? And the omega is the particular group cocycle, a 3 cocycle. That is nothing, that keeps track of nothing but the anomaly associated with this Z2 symmetry. in the sense that if this omega is Z2 valued, and if this omega is trivial, then we know it's consistent to gauge, and if omega is non-trivial, there's an obstruction to gauging, in the sense that you will not be able to get a consistent theory. So let's see that in motion. So suppose you want to let's study this gauging process in the concrete observable. You can of course study in the general observable. Let's study the concrete observable, namely the torus Penning function of a corresponding theory T. Okay? The torus Penning function of the theory will denote the gauge theory by T mod D2. T is the original theory with Z2 symmetry, and denote the putative theory obtained by gauging D2 as T mod D2. The torus Penning function intuitively is built out of the following blocks that come from the original theory, the torus Penning function of the original theory, decorated by the topological defect that generates the Z2 symmetry. This is the kind of combination of torus Penning function. So this is the torus Penning function just for the original theory, okay, represented as a box, as something you usually see in the 2D CFT textbook. And these other configurations keep track of where the topological defect is inserted. For example, here the topological defect is inserted in the time direction. So this is the thermal Penning function with respect to the Z2 twisted sector. And this is when the topological defect is inserted in the spatial direction that implements the Z2 charge acting on the Hilbert space before you do any twist. And this is the mixed sector, where it tells you how Z2 symmetry acts on the Z2 twisted sector. Okay. And this is the kind of configuration that you write in general with coefficients a priori unknown. Okay, so this 1/2 is just because I know the answer, I put 1/2 in the front. But in principle, you are supposed to. So these 4 blocks are the most general background that you can write for a Z2 symmetric theory. Okay, and your task to find the consistent theory is to ensure that you can find the combinations of these building blocks such that it satisfies desired property for the quantum field theory. And here, the desired property we're going to use is a consequence of locality, namely the SL2Z invariance. Okay, SL2Z invariance of the 2-dimensional CFT is nothing but locality that's coming from cutting the torus in either spatial or temporal direction, okay, within a particular device of frame. Now, from this picture, you already see these 2 blocks are tied together by a modular S transformation, and this is obviously modular S transform invariant by itself. Okay, so these 2 coefficients have to be the same, and using the fact that this picture is related to okay, so that's sufficient. So the condition we want to, and this is obviously S invariance, and what we want to ask from this diagonals is to look at this final block and ask whether it's S invariant. Okay? And this is where we may run into trouble because there's different ways to resolving these 4-fold junctions. Either as this, or is this part still visible? Okay. Or as that. Okay. Okay. The point is that for the topological junction associated with this discrete group-like symmetries, the junction vector space is 1-dimensional. So either basis will suffice. Okay, so this is 1-dimensional basis will represent this junction, similar over here. Okay, and obviously these 2 are related by S transformation, which just rotate the diagram by 90 degrees. But if these 2 are not equal, then we're in trouble. And indeed, the relation between the 2 is precisely omega. Okay, so in other words, we cover that if omega is equal to 0, the condition that logically conclusion we follow is that if omega is equal to, in my notation, in this notation is -1 to omega. If omega were to be equal to 1, it means that we fail at building a consistent quantum field theory, no matter how hard we try, by starting from the general building blocks that as decorating the torus Penning function with the background gauge fields. Okay. But if omega were to be non-zero, omega were to be 0, okay, then I will not do the exercise on the board, but you can convince yourself that indeed you can implement the gauging consistently. And what you find is precisely this combination where all the coefficients over here are set to 1. And this 1/2 will be crucial to ensure we land in the loop of quantum field theory with the property I mentioned in the beginning, namely unique vacuum. So 1/2 is crucial. And you can re-represent this configuration as something very intuitive, namely projection. So I should have said that once you land on this picture, it's kind of intuitive. Then what you're doing is you're doing projections. So this block plus this block is doing projection on the Hilbert space without any twist, and these two add together are doing projection on the sector with a twist. Okay, so it's intuitive that you can re-represent this combination of Pauli functions as a single decorated Pauli function as follows, where you have this configuration of topological defect labeled by A with particular junction vectors. I'll call it M and M check. Okay, where A is nothing but the projector up to an overall coefficient. Where 1, I remind you, is a topological defect, this trivial topological defect, and eta in my notation here is a Z2 symmetry defect. So that's what's representing these solid lines in this twisted torus square function. Okay, so you can convince you that with this configuration and the property price of M and M check, you reproduce the top expression. Okay, and it's this picture that generalized immediately to gauging generalized symmetries described by general fusion categories. And of course, the consistent conditions that ensures that you have a consistent QFT after this gauging procedure leads to a number of constraints of what A and what M can be. Okay? And together, so consistent theory from this gauging procedure that's at the torus level, just by taking this configuration of topological defects with the particular junctions, okay, leads to the following conditions on this object A and M. So these are, again, topological junction. These are topological defect. And in general, they're not simple. For example, you see over here, it's a direct sum of two topological defects, the trivial one and the Z2 generator. You can think about this kind of, roughly speaking, as projector. Okay, but of course, it's a projector up to overall scaling. And the consistent condition will be consistency condition on the projector when you have projector both in the time and spatial directions. And this full set of consistent conditions leads to mathematically this notion of a symmetric, a separable Frobenius algebra object in the corresponding fusion category C. Let me just give you some intuition for the corresponding conditions. So these conditions are known as algebra conditions. They are just consistent conditions for this gauging procedure to produce a consistent QFT, namely the locality property. So the condition that you want, for example, is that if you have this configuration of topological defect, it has to be invariant under this following crossing move. And this is intuitive from the group-like symmetry case, because these two configurations are related by a change in the trivialization or a local gauge transformation. And for the gauging to be consistent, your background, your Pauli function must not depend on this background in a non-trivial way, meaning that trivialization should lead to the invariance property of your decorated Pauli function. Okay? And in this particular case, if you look at the torus, where you have this kind of configuration, M check and M, M check and M, which are potentially different topological junctions. And you have the similar property that you can reconnect them like this. Okay, I think I'm going to stop the combination here and then check. Okay. This is related to the Frobenius condition, and this condition is needed in order for this configuration to satisfy SL to Z invariance. Okay. Here, just for the S invariance. And there's a number of other conditions that fully spells out these words, but I will not have time to explain them in detail, but all they capture is just the algebraic properties associated with this topological defect and this topological junction, such that you produce a healthy CFT that's consistent with unitarity, locality, and also the uniqueness of the vacuum that I said in the beginning.
This is just at the level of the torus partition function?
Sorry?
Is this just at the level of the torus?
No, for all observables.
No, but is this condition that you inferred from the torus partition function
This is from the torus partition function.
sufficient?
Together with this, and what I didn't write for the M perps, they ensure that all observables are consistent. So that involves kind of more cyber type analysis. You have to study the basic moves for change in the cutting and gluing, and you can prove this is the case. Okay. All right. So now I have introduced this notion of generalized gauging. What's the question I want to ask and address over here? So the question is that given a C symmetric, given a QFT that is with a symmetry which is described by a subset, like say for stability, described by a finite subset of what the defect line in a given theory, and that subset is denoted by this fusion category C. Okay? What are the possible gaugings that you can implement? Okay, this will be a direct generalization of the usual notion of discrete torsion for overfold. Okay, with different possible gaugings. So first, you have a notion of subgroups. If you have a group symmetry, there are subgroups that you can gauge. And furthermore, for a fixed subgroup, there is a possibility of discrete torsion, and all those different choices have a generalization that leads to this notion of possible gaugings associated with the symmetry category C. And furthermore, you want to ask, what is the dual symmetry in the gauge theory? So if you know your theory has the symmetry, and you know a way to gauge, can you immediately tell me what is the symmetry in the dual theory? In the overfold case, this is known as the quantum symmetry. And again, there's a direct generalization for gauging generalized symmetries. And furthermore, as you know from the overfold case, if you have a discrete group-like symmetry, for example, if it's a abelian, the quantum symmetry is isomorphic to the abelian group that you start with, and you can gauge that the quantum symmetry is isomorphic to the abelian group that you start doing the overfold with. And if you gauge this quantum symmetry abelian group, you return to the original theory. So the gauging can always be undone by gauging the quantum symmetry. And you want to ask if the similar statement is true for generalized symmetries. And furthermore, you can ask, what about sequential gauging? And many other things that you like about gauging ordinary symmetries. Okay, and the short answer is that all the answers to these questions are essentially contained in the work in mathematics on category theory. In particular, the study of what's known as module categories associated with the fusion categories. But we are physicists, so what we are striving to understand over here is to provide a physical picture for all these ingredients associated with generalized gauging. And the main message we want to get across is this equivalence way of thinking about generalized gauging in terms of topological interfaces, which is a direct generalization of topological defects that describe generalized symmetries themselves. Okay? So topological interfaces, you can think about as instead of topological defects, which are codimensional objects that are topological in the given quantum field theory, topological interfaces are just topological objects, codimension one, that interpolate between one quantum field theory to another. Okay, so in particular, topological defects are a special type of topological interfaces in the same quantum field theory. And along the way, we'll see precise realizations of the gauging procedure in two-dimensional CFTs. Okay, some more non-trivial than the others. And we'll also give physical derivations, simple physical derivations for mathematical properties of the notion of module categories. logic categories. And furthermore, we'll derive some bootstrap. So once you have this connection between gauging and topological interface, you can try to classify possible gaugings by classifying topological interfaces. And there's a bootstrap type argument for this classification. Which I probably will not have time to talk about in detail. I'm happy to talk right now afterwards. And finally, deduce from this classification results constraints on RG flows, which you can think about this generalized gauging as giving you a way to predict the family of RG flows, giving one RG flow that has that symmetry. So let me try to explain this main message, namely this equivalence between generalized gaugings and topological interfaces between two-dimensional quantum field pairs.
Hi, I want to ask.
Yeah.
When you say gauging, are you allowed to add additional like topological degree of freedom on the topological data? For instance,
Yeah, counter terms. You can add counter terms. Yes.
Oh, I'm not talking about counter.
Yes.
So I'm asking about decorating the topological data with a TPRT.
Sorry, the total.
I'm asking about decorating the topological data with a TPRT.
Sure, decorating the.
The topological data. It's not the topological data.
Yes, yes.
Can you modify it by decorating with a TPRT?
You can. So the one so for example, the algebra objects. Okay. In general, you can write things like this. Okay, and so on. Where this is simple topological defect and this is degeneracy. And you can think about this degeneracy as coming from topological quantum mechanics.
No, but in general, you will have like you kind of make a way to like gauge.
You can, yes.
I mean, for instance, even in the Z2 case,
Yes,
like with non-trivial omega,
yes,
you can decorate the topological different like with a projective condition as Chromos doubly to cancel the like.
that will require you to have a non-degenerate vacuum. But that will you have to
that's
require
really on the line, right? I mean, I'm only introduce additional degree of freedom on the line, not in the bulk.
No, so for the Z2 symmetry case, there's definitely the answer. There's a unique topological defect you can gauge only when omega is equal to 0. And just 1 plus the Z2 generator, there's nothing else. Okay.
Well, in general, you can decorate. If you're allowed to decorate the topological defect with
Yes.
TPRT, you can cancel some of the gauge anomaly. In particular, for discrete symmetry.
No, I'm talking about bosonic case. Okay. And in this case, there's no additional modification you can
In
do.
general, that can happen.
In general, it can, but for Z2, it cannot.
And you're allowing such cases.
Yes, I'm allowing such general possibilities. Yes. All right, so let me first explain the way we go between these two notions. First, from gauging to topological interface. Okay. So because the discussion I'm going to have is very general, it does not rely on details about how you construct this topological this algebra object. So let me first establish this direction. This is relatively simple. So the idea is that as I explained, the gauging procedure in general come from algebra object and the corresponding topological junctions that satisfy a bunch of consistent conditions. But for this purpose, it's very simple to cook up the topological interface. So what you can do is you consider a particular space-time and fold into two halves, and you do what's known as a half gauging. You gauge this topological defect A on half of your space-time. So you have your theory over here. And here you have your gauge theory, which is denoted in this intuitive way. And what this means, what this half gauging means, is that you have dynamical gauge field, A gauge field, discrete gauge fields on the right-hand side, and you impose a derivative bounding condition for A. Okay, this is put a quotation mark because it's the intuition really comes from the group-like symmetry case, but there's a precise generalization for the generalized symmetry. And what this half gauging does is because, so first of all, this is a discrete process. So this will give rise to a topological interface between the original theory and the gauge theory. So what it gives rise to over here is that a topological interface between the theory T and another theory, which is the gauge theory. Okay. And in particular, this topological interface has this property that if you use a topological interface and its orientation reversal, which is the topological interface between the gauge theory and the regional theory. The picture you should have in mind is that you have gauging in a strip. Okay. And if you think a little bit, what you obtain when you shrink the strip, because the interfaces are topological, what you obtain is just gauging in this very thinner and thinner strip. And in the end, what you get is nothing but the algebra object itself, okay? Which is like implementing the projector in this direction. And in the spatial case, when the two theories are isomorphic, okay, when the gauge theory and the original theory are isomorphic, this interface becomes a topological defect in the original theory T, and this leads to the notion of the self-duality defects for generalized gauging. That's also studied in Jinbi's paper with other collaborators. Okay? In particular, the Tamura-Amagami fusion category symmetry arises in this way. So in view of time, let me skip on explaining the other direction and just talk about one example. I think I have 5 minutes. Right, so in view of time, let me skip the other direction and talk about just one example. Okay, so the particular simple class of algebras you can imagine is a direct generalization of Z2 symmetry. Remember, in the Z2 symmetry case, the algebra object that implements the conventional Z2 gauging is just the trivial topological defects direct sum with the Z2 symmetry generator, which is nothing but the projector. You can generalize this to the case of the general fusion category, okay? And imagine that you have, again, you always have the trivial defect, but imagine you replace this Z2 generator, which in particular satisfies the trivial fusion rule, by a topological defect that has non-trivial fusion rule. Okay? And this we denote by this analogy as a binary algebra. It's like gauging two things. Okay? And in this case, the algebra conditions are particularly simple. So the algebra conditions are very simple. The separable Frobenius algebra conditions are very simple. In particular, you need the following condition. So remember, I have this condition. So I just draw in the upside down fashion by this equivalent. That this better be the same. Okay. In order for this to be a correct algebra object where topological junctions are M.
Guess they mean the other way around.
Yes. Otherwise, a trivial equality. In this particular case, when A is the direct sum of the two, you can spell the left and right hand side. And what you find is the following. Equal to, okay, where there's a numbers that depend on the choice of topological junction over here, square all the topological junctions essentially, which I'll write as alpha and beta. It's the same number because it's the same type of topological junction that appear here and here, here and here. Sorry, here and here versus here and here, and here and here versus here and here. Okay, the same product of m's, this m coefficient shows up, and then denoted by alpha and beta. Okay, and this is a non-trivial equality because each of this configuration of topological defect lines are related to one another by the f symbol, f moves. Okay, for the invertible case, you only have these two. On the left-hand side, this diagram is 0 because each individual solid line would represent a Z2 generator, and there's no topological junction involving 3 Z2 generators, obviously. So you don't have this diagram, you don't have this diagram. So what I'm saying is that if it's invertible, then for this equality to be consistent, that you find these two diagram has to be the same. Okay. And these two diagrams are precisely related to one another by a change of a trivialization, which you can imagine doing in this region, for example. So reconnect the external points. And this condition is equivalent to the condition that omega, this anomaly associated with the invertible Z2 symmetry being 0. Now, the more interesting case is when the topological defect is non-trivial. Sorry, non-invertible. Okay, so means it's bigger than 1. And the same simple example you can imagine is actually in the Fibonacci category, which is generated by two topological defect lines, denoted by 1 and W, where the fusion rule is W squared equal to 1 plus W. Okay. And this is the symmetry. This is known as part of a symmetry associated with, for example, a triangularizing model, the G2 level 1, W model, F4 level 1, W model also exists in EA level 1, CFT, and many others. And whenever you have this symmetry, you can imagine an algebra object of this type. Okay. When, as I said, for this simplicity, let's focus on the case where it's just 1 plus the simple topological defect W. Okay. And then you can try to find if there's a solution to this equation for alpha and beta that's consistent with the F symbols. And indeed, there's a solution. And this is no surprise because A is equal to W squared. Okay. And I didn't have time to explain that, but it happens in general if A is a fusion product between two topological defects. A topological defect is dual, here W with itself. You are guaranteed to have a well-defined algebra structure, essentially because you can think about A as starting from this. You can fatten everything. So this is very interesting. So you can fatten everything. So if A is equal to W squared, you can fatten everything, and this condition becomes trivialized. Just as different ways to deform your favorite dough. Okay, so even without doing any calculation, you know this is defined the algebra object. And furthermore, the fact that it's coming from just this your dough deforming this way tells you that if you have a theory with the symmetry given by the fib, and if you gauge this algebra A, you're guaranteed to have the same theory back. So in other words, any quantum field theory that has this fib symmetry is guaranteed to be self-dual when you gauge this algebra, the binary algebra object. Okay. And there are many other generalizations of this binary algebras that allow you to connect different SU2 WZ models. For example, the ADE modular invariants of SU2's WZ models are related to the A-type modular invariant by gauging certain binary algebras. And there are more interesting algebras if you go beyond this specific class. But there are extensive discussion in our paper and also in Jendy's paper in the particular case of Rev H8. I'm happy to explain to you afterwards. Let me just end by saying a number of future directions. So one thing I didn't talk about is this bootstrap procedure to classify topological interfaces. And using that procedure, we have classified topological interfaces for a number of low-rank fusion category symmetries. And furthermore, there's an interesting story of thinking about this generalized gauging, not in 2 dimension, but in higher dimension. And a starting point is to think about generalized gauging in 3-dimensional topological QFDs, which we also made some progress. In that case, you'll be gauging certain condensation defects. Okay, and then there you don't require the physicalness anymore. And as I also mentioned, there's an interesting RG flow constraint you can deduce from this classification results. First, by the angle, by the connection between module categories or topological interfaces to the TFTs using the slab construction. And second, by this relation between different RG flows that preserve a given fusion category symmetry, okay, by the generalized gauging within that fusion category. And lastly, I should mention here, I focus on the topological interfaces in 2-dimensional QFT. There's a much larger class of interfaces in 2D. They're, for example, conformal or not. And it will be very interesting to understand the generalization of this fusion structure, okay, associated with this more general interfaces. Let me end here. Sorry for going over time. I'll take questions.
So in general, what is the quantum symmetry that you get? I mean, here in this case, I mean, it's the same sense, right? You get the same theory.
So if you get the same theory, then the quantum symmetry you get is isomorphic.
Yeah.
But in general, the quantum symmetry you get will be what's known as a dual fusion category. And it has very nice feature in the sense that the amount of topological defect is conserved. Okay, but in general, it will be a different fusion category, unlike for the abelian group case. And the simplest case you can imagine is you have a non-abelian symmetry, and when you gauge that, the quantum symmetry is rep of that symmetry, rep of G. Okay, it's different as a fusion category, But if you look at the total quantum dimension, namely the sum of the squares of the simple topological defects, you will find the same number. And in this context, the way you discover the quantum symmetry is by fusing these topological interfaces in the opposite way. Okay. So I didn't explain. You can, but you see over here that you can recover the algebra.
Engaging in.
That's right. Okay. So many of the algebraic properties associated with fusion categories and the module categories, which captures the different gaugings of fusion categories, are captured by these topological interfaces and how you fuse the topological interfaces. For example, sequential gauging is naturally given by the fusion of the topological interfaces, and undoing the gauging just corresponds to considering the orientation reversal of the given topological interface.
Say a bit more about the 3D case. Gauging condensation defect.
Right. So the simple example you can consider in 3D, which people understand very well, is the following. So in the 3D dimension, for example, there's a relation between MTCs by condensation, which correspond to essentially gauging one-form symmetries. And the simple example is presumably going from like Torrey code, okay, the D2 gauge theory, to the trivial MTC, like even level 1. And then you can do by condensation of the Lagrangian algebra, like 1 plus E or 1 plus N. Okay, that's gauging one-form symmetries, E to one-form symmetries. But to go backwards, you need to gauge a condensation defect. You gauge a zero-form symmetry. And there are similar stories. There are many more non-trivial examples. That's the example that people understand. Essentially, the class of so-called G-crossed MTCs.
Well, a simple like non-condensation example would be like start from a free Maxwell theory in 3,000
Yes.
circle, and then you got something readable dimensional, which is non-condensation.
Sorry, 3 plus 1 on the circle.
I mean, yeah, 3 plus 1 dimensional.
Yes.
A suitable coupling has non-readable domain wall,
Yes.
and then reduce the theory on the circle.
Yes.
And got a 2,000 theory with non-readable domain.
Yes. It's not a yeah. So in that context.
The domain wall is not compensation.
That's right. That's right. So you want to ask, I see what you mean. So you want to ask, how do I gauge that those zero form of symmetry in that context?
Yeah, for instance.
Yes. Yes. That's a good question. I don't know the answer.
So you imagine this 3D Maxwell scale.
It will be like the compact boson plus like. So I guess you can dualize two. I can say it's just functional compact boson.
Yeah.
So dualize the U1 gauge to compact boson as well.
So,
Yeah.
and then you reduce the duality. And then
Well, you can use many. Well, it depends on which coupling you run with. For the
Yeah, I should say that there are much to be explored in this generalized gauging stories for general higher dimensional theories. Already, as we saw from Portion's comment, beyond MTCs in 3 dimensions.
But I think Wang and Kong already has some papers about like describing generalized gauging for
MTCs.
Not just MTC.
Yes.
For general topological order. I mean, they have some abstract math paper.
From Wang and Kong.
I mean, maybe Wang and some other people. Yeah.
I don't think so. So in the MTC literature, the most
I'm not talking about MTC. I'm talking about like general topological order.
yeah. So in particular, it includes MTC.
Okay.
Yeah. So I'm saying that in MTC, the only works that I know that discuss this is from Runkel and I forgot. Yeah, I'm sorry, I forgot Victor. I forgot the last name. Anyway, so they define the procedure, what they call is optifold dictum. That's associated with the MTCs you can gauge to essentially obtain any dream field doubles starting from the trivial MTC. Okay, but that's the most recent work I've seen on this topic. So of course you can do condensation from dream field doubles to the trivial MTC. What's slightly non-trivial is to go backwards. That involves gauging this condensation. And they explain this in this language of overfold data. which is some generalized data you put in to implement this zero form gauging. They don't say in this language, but I think this is what they mean.
But in that portion, you put in the twist effect by hand before you run this data.
Sorry?
In that paper,
Yes.
you have to put the twist effect by hand before you use their algorithm, right?
The twist, sorry, what do you mean by putting the twist effect by
So when
hand?
you try to gauge a zero form
Yeah.
symmetry, the surface operator can end on some line.
That's right.
After you gauge it,
Yes,
it becomes-
exactly. Yeah, so that's.
I think that's something you have to put by hand. It's not included by the procedure.
You think it's additional information?
I feel like
Well, I see what you mean. So roughly speaking, you need to engineer a greenfield double. You need to put in the fusion category by hand. That's in the twist sector. That's what you're saying.
yeah, something.
But my impression is that that's part of the. Okay, you say it's not part of the data. Okay, that I'm not sure.
Yeah, I'm very
Yeah.
confused by the direction. But
Okay, but you know the paper I'm
Whether-
talking about. Yeah.
That seems analogous to how when you gauge G, you can have to go flow cycle.
What is the?
There will be some equations, cycle equations, but gauging the is this orbital datum.
Yeah. You mean?
So it's very similar to like when you gauge G.
Yeah.
Say, I know what G symmetry is.
Yeah.
There's different ways of gauging.
Yes,
right?
yes.
So saying what TQFT you get after gauging is not well defined unless you.
Yeah. So that's what I was. Yeah. But I sympathize with Jindy's comment because when I read when they have this huge bracket of the data in this orbifold datum, I see nowhere the fusion category is inputted. Like they have this long bracket. It's not just A and M. They're like maybe 6 things.
I mean, here it's actually also.
I know, but there still it's
There's a
longer. Yeah.
guarantee you only need the-
Okay. Yes. So here, indeed, for the experts, there are more potentially more data you to specify here, but for the unitary context, everything else is fixed just by this data. So I'm using that to simplify the presentation. But it can be generalized.